All right, welcome to the next meeting of the New England Dynamics and Number Theory seminar. So Felipe will tell us what to expect today.
Yes, thank you, Dimitri. Welcome, everybody. Today's speaker is Emilio Corso. He joins us from ETH in Zurich. He'll be speaking on the asymptotics of the equidistribution rate of expanding circles on compact hyperbolic quotients and applications. Emilio, the floor is yours.
Thank you very much, Felipe, for this introduction, and thanks, Dima, for offering me this opportunity to give a talk in this seminar. I think that speakers usually here use slides. However, I chose to depart somewhat from this tradition, as just recently, last week, I once again, after a long time, had the experience of the beauty of a genuine Blackboard talk, and right now I shall try to replicate this as much as possible. So the topic I would like to address today is part of a broader program, which currently lies at the core, I would say, of the research area known as homogeneous dynamics, which aims at providing quantitative, effective analogs of well-known and foundational results in the field, which have found a number of applications in number theory, but certainly beyond that. But before confining myself to the concrete case, which appears in the title, I will give a brief overview of the class of examples that have motivated our work. So the new results I will present today are obtained jointly with Ravotti, who is in the audience today and is currently a postdoc at the University of Vienna. Let me start with an introductory section, trying to compare, to relate two fundamental dynamical properties, which are, so let me start with section one, an introduction. So the two fundamental properties are mixing and equidistribution. I shall place myself directly in the setup I will be interested in throughout the talk, in the general setup. So I will be dealing with group actions, not just discrete dynamics or flows. So let me give the definition, recall the definition of mixing for group actions. Let G be a, say, a locally compact group, locally compact topological group acting by measure preserving transformations of a probability space say x a mu. The action is mixing. Well, it's just the obvious transposition of the usual notion for flows and discrete dynamics if for any pair of measurable events, A, B, sigma algebra A, the limit as G goes to infinity, G being an element of the group G of the measure of the image of A under G intersected with B is equal to the product of the two measures, mu of A times mu of B. Namely, this sets GA and B become asymptotically independent with respect to mu as G goes to infinity inside the group, or if you want, in the one-point compactification of my locally compact group G. Now, mixing is a very desirable property to have for a group action for a number of reasons. First, it implies ergodicity, but actually much more than ergodicity. It implies that clouds of initial points tend to distribute uniformly with respect to the measure that we have at hand inside the space X. And more specifically, if you take a positive measure subset A of our space X, and you consider the measure, the normalized restriction of the measure mu to this set, well, the push forward of this measure under the action of G as G goes to infinity will converge in the weak star topology, hence we say it equidistributes towards the measure mu. And this follows directly, essentially, from the definition of mixing that I just gave. So in other words, just to say it briefly, mixing implies equidistribution of positive measure subsets. Now, a natural question arises at this point, which is of interest both from a theoretical perspective, let's say, but also in light of applications, namely what happens to thinner subsets, meaning sets which are negligible from the point of view of the measure mu, but have some relevance for the dynamics. So what about thinner subsets? And here I'm talking about subsets which support a natural probability measure so that we can talk about equidistribution. An example of which could be maybe a parametrized curve, but actually I will directly deal with the general source of examples, which encompasses also the concrete case of expanding circles, hyperbolic circles, that I will be dealing with afterwards. So an example, very general example coming from, it's a typical example of homogeneous dynamics. Typical question in homogeneous dynamics is the following.
Excuse me, Emilio, can I ask
Sure.
something? So on my screen, somehow your video feed is intersecting with the slides. Maybe you can control it somehow, because I don't know how to do it. Do you see it also?
I also see it.
This window takes part of the screen. I don't know why.
So
maybe there is nothing.
I also don't know why, and honestly, I don't know how to fix this.
Okay.
So
maybe
I shall try to keep the slides, not to scroll down too much slides so that it affects as little as possible.
Yeah, well, all right. Maybe we can live with that.
Yeah, okay. Thanks for pointing this out. I'm sorry, I don't know how to handle this. The first time actually that it appears. So this example about homogeneous dynamics. So let's suppose now that G, say, is a locally compact second countable, let's say, topological group, and our space X is a homogeneous space. So X is gamma mod G, where gamma is a lattice in G, meaning clearly that it's a discrete subgroup of G such that the quotient X carries a G invariant Borel probability measure. So this is my ambient space. What is this thin subset I could be interested in? Well, let's take H to be a closed subgroup. Assume that the intersection gamma with H is a lattice in H. So this closed subgroup intersects gamma in a lattice. Well, under this assumption, the H orbit, so G of course acts on X by right translations, and the H orbit of the identity coset of gamma, which is the identity coset in my space, in X, carries a natural H invariant measure, carries an H invariant probability measure. Which I will denote by M H dot gamma to indicate that it sits uniformly inside the H orbit of gamma. This is just the push forward under the orbital map, or the map induced by the orbital map of the natural invariant measure on the homogeneous space H mod gamma intersected with H. And the question is, assume that the G action by translation of X, that G acts mixingly on X with respect to the H measure, Hasegal measure, mx, so the unique G-invariant measure on X. And the question is, do the push forwards by G of my measure sitting on the lower dimensional orbit equidistribute towards the H measure? Towards mx as G goes to infinity in my group? So that's the question. So you should think about these measures as H measures sitting on lower dimensional, uniform measures sitting on lower dimensional submanifolds of my space X. And what we are really asking here is, how does this submanifold evolve somehow under the dynamics given by the G action as the element of G goes to infinity? Does it remain for some reasons confined in some region of the space, or does it sit uniformly, ever more uniformly as the dynamics evolves? And well, there are obvious obstructions to this, meaning, namely, for instance, if you assume that there is some other subgroup, intermediate subgroup L, which contains H and intersects gamma in a lattice, and say L is non-compact, then of course, when you go to infinity inside L, you will be trapped inside that region. You will not distribute uniformly. But if you rule out somehow this obvious pathologies, actually, this equidistribution statement turns out to hold under quite general favorable circumstances. And the first example that has been historically completely worked out of this phenomenon appears in the PhD thesis of Gregory Margulis in 1969, although it has been published much later. And it's precisely the concrete example that I will be dealing with, namely large hyperbolic circles. However, before turning to this example, perhaps at this point, there is the work of Eskin and McMullen that deserves mentioning, because it somehow it's, roughly speaking, the state of the art concerning this problem, although it dates from the 1993, and which gives you quite general assumptions under which this equidistribution statement holds. Namely, suppose that G is a connected semi-simple, well, real, only dealing with real Lie groups today, real Lie group, say with finite center. And assume that H is the fixed point set of an automorphism of G, of an involutive automorphism of G. So this is a setup that generalizes Riemannian symmetric spaces. The quotient G mod H would be called in this case an affine symmetric space, automorphism of G. And let's take gamma to be an irreducible lattice. Well, under these assumptions, the action is mixing, the action of G on G mod gamma is mixing, and then equidistribution holds. And it is derived from mixing via a thickening argument, so-called banana trick of Margulis, from mixing via a thickening argument. So this should come as no surprise, given what I said at the beginning. Mixing is just equidistribution of thick subsets. And now that you want to deal possibly with lower dimensional subsets, what you do is, it's not surprising, you try to thicken them into some positive measure subset and then use mixing. Of course, in order to do this, your space G mod H has to be has to satisfy certain properties. G mod gamma has to satisfy certain properties, certain geometric properties. In principle, so by a thickening argument, which is originally due, I should write, due to Margulis. 1969. Now, theoretically, this thickening argument, so taking this lower dimension submanifold and thickening it into a neighborhood, would give, is amenable to be transferred to the question of effective equidistribution, namely providing some rates for the equidistribution of this translates of H orbits, provided, of course, that you know a statement, an analogous statement, quantitative statement for mixing. So if you know effective decay of matrix coefficients, effective decay of correlation, you can in principle transfer this quantitative statement to equidistribution, but there might be some loss in the exponent that you get when you replace a lower dimensional subset with the thickened version. And this loss has to be controlled and depends in general on the geometry of the space that you are working with. That's why we chose a different approach, which is of spectral nature. And now it's, I believe it's time to get into at least the setup of the concrete example that I want to deal with today, which is expanding circles on compact hyperbolic surfaces, or rather on unit tangent bundles of compact hyperbolic circles. So let me say that let me choose S to be a connected compact hyperbolic surface, orientable maybe, hyperbolic surface, which hence it as a Riemannian metric, giving it a sectional curvature constantly equal to -1. So as it is well known by the uniformization theorem, S is as a Riemannian manifold as isomorphic to a quotient gamma mod H, where gamma is a co-compact lattice in SL2R, and it acts by isometries on the universal cover of S, namely the hyperbolic plane on HG, where H is the, let me choose the upper half plane model of the hyperbolic plane. So it's the set of complex numbers with positive imaginary parts, and G is the hyperbolic Riemannian metric given by dx squared plus dy squared over y squared. So this metric gives the hyperbolic half plane constant curvature equal to -1 and descends to an analogous metric, to a metric possessing the analogous property on the quotient by gamma, since gamma acts by isometries. Now, under this identification, we can identify also the unit tangent bundle of S, which is so the set of points, the set of unit tangent vectors belonging. So it's a set of elements in the tangent bundle such that of norm 1. Well, it becomes identified with the homogeneous space gamma mod SL2R as the unit tangent bundle of the hyperbolic plane itself is identified with, well, PSL2R, but I don't want to deal with PSL2R. I directly choose SL2R for simplicity. Now, the geodesic flow on the unit tangent bundle is, I mean, very well known in this audience. Let me call it phi t x. Well, is defined geometrically as the flow which moves any unit tangent vector at unit speed along the unique geodesic it defines on the underlying surface. But actually, the peculiarity of the hyperbolic setup is that it can be conveniently realized as in an algebraic manner. So it's defined as, so phi t x, the transformation from, so let me call this homogeneous space in the sequel M for simplicity. So it simply sends a right coset gamma g to the right multiplication by the matrix, diagonal matrix e to the t halves, e to the minus t halves, which is nothing but the one parameter subgroup of SL2 generated by the matrix 1/2 minus 1/2 belonging to the algebra of SL2. That's the algebraic description of the geodesic flow, and what I'm interested in are circles, namely orbits of points in my unit tangent bundle in this homogeneous space under the action of the maximal compact subgroup SO2R. So let me define for any S in R the transformation RS from M to M, which is simply right multiplication by the matrix, the rotation matrix. So sinus of S halves, I chose this normalization only for convenience in later computations, but it's just a parametrization of SO2R. And this is, again, it's a one parameter flow on this homogeneous space because it's simply exponential of S theta, where theta is another element of the algebra given by this form. Now, if I fix, if a point P, which is a couple ZV in my unit tangent bundle is fixed, what is the collection of all its transformed transformations by RS? Well, this is simply, this parametrizes the unit tangent space at that point. So it parametrizes T1Z of S. So I have all the unit tangent vectors at my fixed point Z, a fixed base point on the surface. And if I let now this set evolve under the geodesic flow, and for any T in R, say positive, the image of this set under the geodesic flow, well, I'm flowing with the geodesic flow up to time T, starting from all possible vectors, from all possible unit tangent vectors at my point. Hence, it's very easy to see that, well, at least in the hyperbolic plane, I get the circle, the hyperbolic circle of radius T, centered at the point Z, with outward pointing normal vector. Well, here, actually, I'm quotienting by gamma, so let's say that this projects onto the surface, onto S, to the image, say, of the image which I call S, calligraphic SZT, of the hyperbolic circle of radius T centered at Z, seen as in the hyperbolic plane, but then afterwards projecting to the surface. And so here, I think a picture and say, so this image projects onto S to this, and with outward pointing, it's, after all, it's a collection of tangent vectors, so it's outward pointing normal vectors. And perhaps a picture, I should have it here, is convenient. So here for simplicity, I'm not drawing a compact fundamental domain, but just the standard fundamental domain for SL2Z, which is not covered by the results of this talk. But anyway, just so that you have something more familiar. So that's in blue, I denote a circle, a hyperbolic circle centered at the point I, which is marked here in the hyperbolic plane. And then in yellow, you see how it falls on the fundamental domain of the hyperbolic of the modular surface. And this picture should somehow give you a rough intuition about the validity of the theorem that I'm just about to state, which is that and is due to Margulis, the non-effective version. The circles, let me call them CPT, so the collection of unit tangent vectors described in this fashion, equidistribute towards the H measure, towards the H measure, which I will denote by vol, which is the unique SL2R invariant measure, probability measure. On my space M. As I said earlier, we are interested in effective rates of equidistributions, but I mean, perhaps it's a good point to stop and ask if there are questions before I move on to the statement of our results. Okay, so I'll just, of course, feel free to interrupt me at any time. And I'll just move on to the statement of our main results, which is an effective and actually a precise asymptotics for this rate of equidistribution. So main result. In order to state them properly, I need to introduce some very elementary harmonic analysis of SL2R. I shall try to keep it at the bare minimum needed for the statement. So let me define a couple of more elements in the Lie algebra. So U is the matrix 0, 1, 0, 0, and V is the matrix 0, 0, 1, 0, seen as elements of little SL2R. They generate the stable and unstable horocycle flow, for those who know it. And once they form a base together with my matrix X, which is the generator of the geodesic flow, they are a basis of the Lie algebra SL2R. And then using the spaces, I can define the so-called Casimir operator. So the Casimir operator, which I denote by square, is given by minus x squared plus x minus uv. And it acts as what is called, well, an essentially self-adjoint operator. Not that I really need this fancy terminology in what follows, but it's just standard material. Self-adjoint operator on L2 of M with respect to the volume measure. So it's just a second order differential operator. So it acts on certainly on C2 functions, and it's an unbounded operator on L2 of M. It is formally it's a generator of the one-dimensional center of the universal enveloping algebra of SL2, which results into is the reason why it's so important in the representation theory of SL2R. In particular, for the moment, I just need the following fact. Since M is compact, the spectrum of the Casimir, which is real because it's self-adjoint, essentially self-adjoint, is discrete. It's a discrete subset of R, and pure point, consists only of eigenvalues.
Can I ask a quick question?
Yes.
So I understand self-adjoint. What is meant by essentially?
Yeah, I won't use this terminology, but it's just when you have an unbounded operator, you can define a closure of this operator. So on the maximal domain of in which it can be extended, and this closure will be self-adjoint in this language. But
okay, thank you.
I'm not using this afterwards. Thanks for the question. So it's discrete and consists of eigenvalues. But if you want to see pictorially how it, I mean, if you want to visualize maybe how it acts, let me just remark that with this normalization I chose, if you take functions which are defined on the surface, not simply on the unitangent bundle, but really on the surface, so they are invariant under the fibers. So on functions defined on S, or in other words, these are SO2R invariant functions on the unitangent bundle. Then functions on M. The Casimir operator acts as the Laplace-Beltrami operator associated to the given hyperbolic metric, associated to the hyperbolic metric S. In particular, the spectrum of the Laplace operator is contained in the spectrum of the Casimir, but it's actually a fact that if I look at the positive part of the spectrum of the Casimir, so the spectrum of the Casimir intersected with the positive real line is precisely equal to the spectrum of the Laplace-Beltrami operator. And this is just to say that we are dealing with an object which has been the subject of the extensive research throughout the years by various people. And sorry, just perhaps it's a good moment to stop again because I need to charge my laptop, otherwise I will lose the connection. Good. Okay, so if there are no questions, let me move on. I can, I guess, finally state my result. So our result. Sorry. So the theorem, to me and Davide. From this here. So let me take a smoothness function. I don't want to be diverted by technical aspects on the regularity, just to tell you that the result actually holds under much weaker regularity assumptions, but let me avoid that and place myself directly into the smooth setup. So let me take a smooth test function on M. Well, then there exists some coefficients, some continuous coefficients that exist for any positive Casimir eigenvalue, for any mu in positive part, strictly positive part. There exists some coefficients d plus mu from M to C, and also d minus mu f. Sorry, should keep track of f also in my notation. Which are continuous, maybe I should say, yeah. Important, at least it ensures that they are bounded on my compact space M. So continuous functions, such that when I look at the average of f over a circle, so I'm choosing in the normalization I chose to get a full circle, I should consider time up to 4 pi. So f on geodesic translate time t of my circle started at the point P. So for any such that for any P base point P in the manifold. Well, I want to get an asymptotic expansion for this expression. So the main term is what we already know by the theorem of Margulis, and that's the global average of f with respect to the volume measure. And then comes a series of additional terms, for which now I realize that I should have defined also. So for any, let me do it here. For any mu in the spectrum, let me define a parameter mu to be the unique element in R positive part union I R positive part. So in is seen as a subset of C, such that U minus mu squared is equal to 4 mu. Now you have the lower order terms of the expansion, and they come from the contribution of any projection of F towards Casimir eigenfunctions. I shall detail this later when I will give some ideas about the proofs, but just to understand at the moment where do these terms come from. So I have a term coming from the eigenvalues e to the minus t halves sum over mu bigger than 1/4. So for those of you who know the terminology, these are the eigenvalues corresponding to the principal series representations of SL2R. So it's I have an oscillatory term here, which is given by the cosinus. So for this eigenvalues bigger than 1/4, my parameter mu here will be purely imaginary. And I have here the imaginary part of mu halves t times this coefficient d plus mu ft plus sinus of essentially the same thing times d minus mu ft. Then I have a contribution coming from the eigenvalues of the so-called complementary series, so the eigenvalues between 0 and 1/4 of e to the minus 1 plus mu halves. Now mu is in between 0 and 1, d plus mu fp plus e to the minus 1 minus mu halves t d minus mu fp. Then there is a contribution coming from the eigenvalue 1/4. So let's say that this term appears only if 1/4 is in the spectrum. So let's say let's multiply everything by the characteristic function of the spectrum by 1/4, and the term now is e to the minus t halves d plus 1/4 fp plus t e to the minus t halves d minus 1/4 fp. And finally, I have a remainder term, which I call rfpt, where now, of course, I need to tell you something about this asymptotic expansion. Well, first, say that this holds for any t sufficiently larger, it gets bigger than 1 suffices, where, well, the infinite sum appearing on the right-hand side converges absolutely, where the infinite sums on the right-hand side converge absolutely, actually uniformly even on M. And I have an estimate for my error term, which is given by a constant which depends only on the surface, and then times some Sobolev norm of f, which I intentionally do not specify, a certain appropriate Sobolev norm of f, times t plus 1 e to the minus t. So it's truly an error term. So this is some appropriate Sobolev norm of f, as it's typical, I guess, in equidistribution statement. Some Sobolev norm of f, and as I said, this constant depends only on the surface. More precisely, it depends on the spectrum of the Casimir on the surface, acting on the surface, and it also depends on some constants given by various Sobolev embedding theorems which come into the proof. So this is the asymptotic expansion that we get. It's a precise asymptotic, and some remarks, I guess, about the statement are in order at this point. So comments. Well, first of all, this improves considerably it improves an earlier result, the result which was shown by Yves Benoit and Theo. I guess it was published in 2012, which only gives, it's an effective statement which only gives the existence of some exponent eta positive, such that the error between the average over the circle and the global average is bounded above by e to the minus eta t. Well, I should also acknowledge that their result is much more general. It doesn't deal just with hyperbolic circles, but that's what they get. They get the existence of some exponent. They don't compute it, or they don't give any bound on it. Well, the second comment is that, well, the statement in particular implies an analog, an asymptotics for the rate of equidistribution. So of course, here I'm dealing with circles seen in the unitangent bundle, but of course I can project them down to the surface. I get what might be called circles again, and they equidistribute also towards the uniform measure on the surface. And so of course, by taking SO2R invariant function, this implies asymptotics for equidistribution rate of large circles on S. A third remark maybe is also that the result holds not only for full circles, but we actually prove it by exactly the same method that I will outline in the sequel for arbitrary arcs of circles. So the result holds for replacing, let's say, replacing any, replacing 4 pi, say, with any theta in 0 for pi. So many pieces of circles actually have this effective rate of equidistribution. Of course, the only thing that changes are the estimates on the error and on the uniform norm of these coefficients, which will additionally depend on theta in a fairly obvious manner. And maybe one last remark is also that the rate of equidistribution matches precisely the equidistribution rate, the mixing rate for the geodesic flow, which was obtained by Ratner. So the rate of equidistribution matches precisely the mixing rate of phi tx obtained by Ratner. In 1956, I guess. So these are some comments I would like to point out about the statement. But since this is not only dynamics, but also a number theory seminar, so far I've essentially dealt with dynamics. Let me mention an application of this result, a classical application of this result, which is number theoretical in nature.
May I ask a quick question?
Yes, please. Hi,
Can
Sam.
you give intuition? Hi. Can you give intuition? So this mu, so from like what I know of like most spectral results, we have this mu equals 1/4 is special.
Yes.
And then we have a discrete component and a continuous component. So can you give intuition for why both of these options for mu are discrete and why they're both infinite?
They are infinite. So there's no continuous part of the spectrum here because the space is compact. So the spectrum is only eigenvalues, only values. There's no if you were to deal with the non-uniform lattice, then you would have the continuous part of the spectrum from 1/4 onwards. But here there is no such thing because I'm dealing just with compact quotients. And indeed, the result should be a similar result should hold also in the non-compact case for lattices, but the proof will be much more involved because you need to deal with precisely with that. That's the additional hurdle that you face when you deal with non-compact quotients.
Okay. And then you said that And the comment you say the infinite sums on the right-hand side, are they both always infinite?
Yes, the sum, well, just one is infinite, the sum above 1/4, and it's always infinite. It's the eigenvalues of the Laplacian which tend to infinity. There's actually the fairly well-known Bayes' law for the asymptotics of the eigenvalue of the eigenvalue.
Okay, so it's just the one sum is infinite and the other one is finite.
The other is finite because it's a discrete set inside a compact interval, so it's there are only finitely many eigenvalues to the complement. Thanks for the question.
Excellent, thank you.
You're welcome. And by the way, since you asked, maybe it's also worth to point out that this remainder term that I get here actually comes from the contributions from the discrete series, namely from negative eigenvalues, 0 and negative eigenvalues of the Casimir. So the Laplace wouldn't have any negative eigenvalue, but the Casimir does have negative eigenvalues. They're entirely understood, they are explicit. And this remainder term comes precisely from the contribution of the projection onto that part of the spectrum of the Casimir.
Can I interrupt also?
Yes, sure.
Just to understand the contribution of the, can you put in the formula for the?
Yes.
Just to try to understand, you mentioned that the sum over the discrete spectrum absolutely converges. My question is, is it true to say that you can bound it uniformly just as some Sobolev norm of your function?
Precisely.
So you'd get an error term which is e to the minus t over 2, assuming you don't have the.
Yes, exactly.
Okay, so those functions are the delta plus and delta minus are explicit enough so you can actually bound them.
Exactly. Yes, they are concrete, fairly concrete, and we can bound them we can bound the sum of their norms over all eigenvalues by a certain Sobolev norm of F. Yes.
Okay.
Exactly. You're welcome. So before saying something about the proof of this statement, let me mention the application to the hyperbolic lattice point counting problem. So the classical Gauss circle problem asks for, so the Gauss circle problem asks for the asymptotic behavior of the number of integer points inside growing balls in Euclidean plane. So the asymptotic behavior of the function cardinality of the set of Mn in Z2 lying inside the ball of radius r, so such that m squared plus n squared is less or equal than r squared as r tends to infinity. So an elementary tessellation argument, which is the one used by Gauss initially, tells you, I mean, you can tessellate the plane by translates of the fundamental domain for the Z2 action, namely unit squares. And this would give you at once both the main term of the asymptotics, which is the volume of the disk of radius r, namely pi r squared, and also a bound for the error term, which is of order r, namely the same order as the growth rate of the boundary of the ball. Now, what I will be, just to mention that, of course, this has been the subject of intensive research afterwards, involving many leading figures in number theory and beyond. And it's known to be perhaps one of the major unsolved problems in number theory. It's notoriously hard to attain the conjectural upper bound for the conjectural best bound for the error on this problem. But I don't want to deal with the Euclidean setup. Let me just directly turn to the hyperbolic, analog of this. So let me denote by n of r the cardinality of the intersection. So I just consider the analog of the Euclidean case. So I fix my base points. I can fix it somewhat arbitrarily, but for convenience, let me say just I look at I in the hyperbolic plane, and I look at the gamma orbit of the point I, intersected with BR, where BR are hyperbolic balls. So BR is the set of Z in the hyperbolic plane, such that the hyperbolic distance, which I denote by d sub h of Z from I is smaller than R. So I look at I want to count the number of, in some sense, integer points, although this has no arithmetical meaning. In general, the number of points in the gamma orbit lying inside the ball, and I want to examine the behavior of this function as R goes to infinity. Now, one can try to transfer the tessellation argument of Gauss to the setup, and at least it provides a rationale for the asymptotics, which is, again, just like in the Euclidean setup, is the volume of the ball, which is proportional to pi e to the r. But it doesn't provide a proof, because in the hyperbolic world, there is an additional complication arising due to the fact that, and this is a typical hyperbolic feature, the growth rate of the length of the boundary of the ball is the same as the growth rate of the volume of the ball. Hence, by performing this argument, you will get a main term which is the same order of the error term, and doesn't lead you anywhere. However, it is by now classical that one can deduce results on this asymptotic once you have results on equidistribution of translates of some orbits. In this case, precisely equidistribution of translates of circles. And so let me say what the corollary of our theorem is. We get the following explicit bound on the error term. So the corollary is, this number of lattice points inside the ball of radius r is, well, first comes the main term, which is pi over, there is a normalization, which is the cardinality of the intersection of gamma with SO2r times the volume, say the co-volume in SO2r of gamma. And then the main term is exponential, just like the growth rate of the balls. And then the error for us is a little o of e to the, well, I have a certain power of r, which is of the following form. So 1 minus 2 over 21, 1 minus, and there is a parameter which I have to explain what this is, mu 0 plus epsilon, all this multiplied by r, and this also for any epsilon bigger than 0, where, what is this mu 0? So where mu 0 is defined as, so let's take mu star to be the spectral gap of the surface S, namely the lowest positive eigenvalue of the Laplace operator. So it's the infimum of spec gamma intersected with positive real part. And let also mu star be the associated parameter, associated value. My mu 0 is simply the real part of mu star. Hence, what is this mu 0? For instance, in many circumstances, compact hyperbolic quotients have only, so the spectrum of the Laplace lies only above 1/4. This is typical and typical behavior. And in that case, mu 0 is just 0. Otherwise, it can be between 0 and 1 if you have also eigenvalues below 1/4, which might definitely happen. And they can be actually arbitrarily small. So this, I don't have time to, to demystify this mysterious appearance of this exponent 2 over 21. Just, I wanted to tell you that it comes from the minimal Sobolev order that we need for the bounds in the equidistribution statement. In order to bound this coefficients d plus mu and also the remainder term, we need some minimal Sobolev exponent. And this, which is, by the way, 11/2, if you're interested. And this 2 over 21 comes partly from this minimal subgroup order needed in the statement. Now, once I state such a result, I should also tell you what's the state of the art concerning this problem. As far to the best of my knowledge, this is the first precise error estimate then that is deduced from equidistribution of large circles. But actually, the state of the art concerning the problem is different. So I don't have time to dwell upon the full history of this problem, but I certainly need to mention the work of Selberg from 1970, which using completely different methods, not dynamical, and by using the deep theory of automotive functions and integral operators, manages to find a better bound for this, obtaining that n of r is equal to, well, same as before, that's the same error as the same main term as before, of course. And then his bound on the error is big O of e to the maximum between 2/3 and 1 plus mu 0 over 2 r. So for instance, if you don't have eigenvalues below 1/4, we get this 1 minus 22 over 21, and Selberg gets 2/3, which is of course much better. But on the other hand, the proof is considerably more complicated, more sophisticated. And let me also perhaps conclude this discussion by mentioning that the conjectural error term is just analogous to the Gauss circle problem, meaning that the error conjecturally should be e to the 1/2 r plus epsilon for every epsilon bigger than 0. But the current best bound that we have, at least on the pointwise error estimate, is due to Selberg, and no one has improved on that so far. Also, perhaps one very last comment is that we might get a better error estimate by trying to decrease the Sobolev order needed in the equidistribution statement, but this would only mildly improve the exponent. And so far, attaining or more pretentiously improving Selberg bound seems out of reach, even in the presence, out of our reach at the moment, even in the presence of such precise asymptotic for the equidistribution. In what remains, let me give you a rough outline of the proof of the equidistribution result. And the method is inspired by the work of Ratner that I already mentioned concerning quantitative mixing of the geodesic flow. For this, I need to introduce a bit more harmonic analysis. So let me also just say right from the beginning that the method is elementary. It uses really basic facts of harmonic analysis of SL2R, and it's really elementary and gives really precise estimates. So SL2, so the measure preserving action of SL2R on M vol, well, gives rise to the Kopman representation. So it gives rise to the unitary representation, which I call ρ, unitary representation of SL2R onto the Hilbert space L2 M vol. And by the general theory of unitary representations, I can actually decompose this representation as in general would be a direct integral of irreducible representations. But since M is compact, I have that my space, my Hilbert space, decomposes as an orthogonal direct sum of over a most countable index set of irreducible subspaces HI. So this means that HI is invariant under the representation for NG in SL2R, and the restriction and rho restricted to hi is irreducible. Now the Casimir, what does the Casimir do? Is that so gamma acts on C2 vectors of L2 and Paul. And if I now look at the action onto each irreducible subspace, well, first of all, I have to recall that it commutes with, since it lies in the center of the universal enveloping algebra, it commutes with all unitary operators, so G. And because of that, and of Schur's lemma for unbounded operators in this case, I get that for any I, there exists some mu I, some eigenvalue of the Casimir, spectrum, such that, well, the Casimir acts simply as a multiple, as the mu I multiple of the identity on, so this is mu I V for any V C2 vector in HI. So on each of these irreducible subspaces, the Casimir acts as a multiple of the identity. So now I can, by regrouping together all those belonging to a fixed eigenvalue, I can simply decompose my space as the sum over all mu in the spectrum of H mu, where these are simply Casimir eigenspaces. So H mu, so for any C2 vector of H mu, the Casimir acts as the mu multiple of the identity. So now, using this decomposition, I can essentially, so the proof essentially reduces, and this essentially means up to non-negligible technicalities, reduces to the case where f, my function f, to the case where my function f is a Casimir eigenfunction. So it satisfies Casimir of f is equal to mu f for some mu lying in the section. Okay, but then in this case, let me write the partial differential equation that f satisfies. It's a second order linear partial differential equation. So I have minus x squared plus x, this is the Casimir, minus uv f is equal to mu of f. Now, the quantity I'm interested in is k, let me call it kft, 1 over 4 pi, remember 0 interval from 0 to 4 pi of f ft of x composed with sp, so f along my hyperbolic circle of radius t. Well, this PDE for f immediately transfers, well, yeah, fairly immediately transfers into a second order linear ODE, ordinary differential equation, for this kf of t, seen as a function of the time t. Because for instance, if you differentiate once this function kf, well, you are taking the, you can move the derivative inside the integral, and you are taking the derivative along the geodesic flow. So there is an xf, x is the generator of the geodesic flow coming. And then if you differentiate it twice, there is an x squared coming. So in other words, this implies that this function kf satisfies the following. So minus k double prime ft plus k prime ft. Well, I bring minus mu on the other side. So minus mu kf of t, well, is equal to 1 over 4 pi, integral from 0 to 4 pi, uvf composed with pi tx composed with ri ds. So it only remains to write this term on the right-hand side in a more in a simpler manner. I mean, using what we know already. So the quantities that we know already. And for this, well, let's write first that v. These are somewhat by now classical manipulations in the using the Lie algebra of SL2 and the algebra of differential operators. So v is I can write it as u minus 2 theta, if you recall the definition of all this vector fields. So UVF is just u squared f minus 2 u theta f. Now, what's the advantage of introducing theta is that, well, theta is the action of a compact abelian group. Is the generator of the rotation flow, SO2R, action of SO2R. So by standard theory of standard harmonic analysis of compact abelian groups, I have that each eigenspace H mu can be decomposed in turn into a direct sum of eigenspaces for theta. So, which I call H mu n, where for any v in C1 of H mu n, these are eigenspaces. So the action of theta on it, well, is because of the normalization I chose, I have to divide by 2 here, and afterwards I have only integer eigenvalues for theta. So again, I can assume without loss of generality, again, up to technicalities which are not immediate to deal with, but without loss of generality, I can also assume, using this decomposition, that f is also an eigenfunction for theta. So I assume that theta f is E halves n f. And so this translates into u f equals u squared f minus I n u f. So I only have to express the integral of uf and u squared of f in terms of known quantities. And for this, I use this trick here, that is, well, if I integrate over the whole circle the derivative of f of my expression, well, I get 0 because of the fundamental theorem of calculus, the integral over a closed circle. But if I now expand this out, what I get, well, is the differential of f applied evaluated at the point. At this point, applied to the tangent vector, which is the differential of phi t x composed S of t. But this, if you compute this using conjugation relationship in SO2R, everything is explicit here because we are dealing simply with matrix multiplications. So there is a general formula here that tells you that this is nothing but the action of the adjoint of x minus tx to the tangent vector theta. So if t is 1, sorry, if t is 0, it's simply theta, it's the direction of the rotation flow. But if you evolve after time t, you have to conjugate by using the adjoint action by x of minus tx. But if you now compute this explicitly using really matrices, this is minus hyperbolic sinus t u plus et theta. And hence, this becomes minus hyperbolic sinus integral of uf, what we want, plus something that we know, because f is now also an eigenfunction for theta. So this is plus et I over 2n, and then the integral of f composed with everything. So this is just our kft. Doing the same. So this expresses this integral here. I'm interested in terms of as linear combination and multiplication by exponential or hyperbolic sinus of functions that I know already. Doing the same for now this time using the same fundamental theorem of calculus, but uf, I reach also an expression for u squared of f, for the integral of u squared of f along the circle. Allows to reach, well, let me say finally what this leads to reach an ODE of the form k double prime f of t plus kft plus mu kft is equal to e to the minus t times a certain function g depending on f t. Well, the essential point here is that this is uniformly bounded in t. And this is completely explicit, meaning that now the solution to the general solution to this ODE has the form, well, you know, the homogeneous polynomial. So the characteristic polynomial associated to the homogeneous version of this equation is x squared plus x plus mu. So it has roots. So the homogeneous polynomial, the characteristic polynomial of this ODE has roots -1 plus or minus mu over 2. And so the solution is given by, is explicit, and it's given by this formula here, where I have first a particular solution which is given in this form, in this integral form. Then I might need to add some constant, some parameter, say C1 for the homogeneous solution, minus e to the minus 1 plus r squared t plus C2, where C1, C2 are complex numbers that I then choose according to my initial conditions that I will impose. And well, this provided, at least provided that mu is different than 1/4, otherwise it takes a slightly different form. But anyway, this is just to say that you get this precise solution, and from that you can really bound everything and define your coefficients and your remainder term. Just to notice that these coefficients here are uniformly bounded by the C1 norm, of my function f. And from that, I can deduce all estimates that I have on the coefficients d plus minus mu and on the remainder term. After that, once you have this result for a joint eigenfunction of the Casimir and of theta, then you add up all the contributions using the decomposition and you reach the asymptotic for arbitrary function. So I hope I managed to convey how elementary, but at the same time powerful, this spectral method is in proving effective equidistribution. In this case, it's really a precise asymptotics. Then the natural question at this point would be, of course, to push it further. First, as I was mentioning earlier, answering to Samantha, that first to non-compact quotients, and then hopefully to higher rank semi-simple groups where the representation theory is clearly more involved, but perhaps sufficiently well understood for this purposes. I think it's time for me to stop, and thank you very much for your attention.
Okay, thank you very much. Why don't we thank our speaker first? And maybe there's time for a question or a comment.
Question.
Oh yes, go ahead, Duby.
Yeah, so can you go back? So my question is in the application to the hyperbolic lattice counting problem, your expansion, your spectral expansion for the distribution has a lot of oscillatory terms. And my question is, do you just bound them by the Sobolev norm and then use some bounds, or do you actually use this oscillation?
We don't use this oscillation. That's why I told you, yeah, this is one of the steps in which our bound is not optimal, absolutely. It's just what we obtained by rather crude bounds right now, and we are currently in the process of trying to improve these bounds. This bound that I just mentioned here is obtained by fairly standard estimates. We are not using anything deep, among which we are not using this oscillation property.
Okay, thanks.
Yeah, you're welcome.
So you mentioned that some natural next questions would be like the non-compact case and also higher rank groups. What about other rank one? Like, for example, expanding spheres and higher dimensional hyperbolic manifolds.
Well, yes, this is also, yeah, sure. Yeah, I just mentioned a higher rank, but this is equally interesting.
Okay.
Yeah, of course.
Okay.
So this method has been, I should perhaps point to some additional history. So this method was initially developed by Ratner, as I already said, but then it was used by Mark in first attempt to show quantitative equidistribution of horocycle orbit. And then also recently by Strombergson on the same problem, and also by Samuel Edwards, who deals precisely with effective equidistribution of expanding translates of horospheres, the ones that you are mentioning.
Mm-hmm.
But I believe what Edwards is doing is, I mean, the philosophy is the same, but he only wishes to have some effective bounds. He doesn't go deep into finding a precise asymptotic.
Yes.
I believe, as far as I recall from his paper.
Okay, so can I ask a question?
Yeah.
Just to, I mean, maybe it's a stupid one. So when you say precise asymptotics, what does it actually mean? So I understand that there are results that you prove, and then there are also conjectures which are stronger. But are there any are there any estimates from below of the error term? I mean, what are the
You
words?
mean in the counting problem?
Yes, in the let's
Yes,
just look at the counting problem.
Yes. I mentioned earlier that the optimal rate.
So how to know what is optimal?
This is e to the 1/2 r plus epsilon for any epsilon. So, you know, in the Gauss circle problem, the optimal rate would be square root of r plus epsilon. I mean, sorry, r to the in Euclidean. And here it's analog with an exponential. So it's e to the 1/2 r plus epsilon for any epsilon. Why is this? Because, well, this is consistent with numerical computations, first. And second, there is work of Phillips and Rudnick from 1993, I guess, in which they prove lower bounds.
Okay, so the lower bounds. Yeah,
they prove an lower bound, yeah, for it cannot be better than e to the 1/2 r. Cannot be better than that. Yes.
Okay, I see.
Are there more questions or comments? Well, if not, maybe we can thank our speaker again. Thank you very much, Emilio.
Thanks a lot to you for the attention.
Very nice talk.